And now I'm going to share the screen with you. All right. Okay, so good. Um, so yesterday, what we did, basically in the last two classes, we discussed the experimental survey of superconductivity. We learned how the superconductivity was discovered and what are its magnetic properties. So by now we know that it's a low temperature phenomena. There are different kind of materials which show superconductivity when they are cooled below critical temperature. And also we saw that when we put them into a magnetic field, so there is a critical field. Above the critical field, they become a normal conductor. And below the critical field, they are superconductors. So basically, magnetic field also breaks the superconductivity, just like temperature. So if you are above critical temperature, it is no more superconductor, it's just a normal conductor. And if you are above critical magnetic field, if you put the superconductor in magnetic field, that's also normal conductor. And in this regard, we explained the Messner effect with the help of macroscopic theory, and that's a London equation, which says that in a superconductor, the magnetic field is not completely zero, but at near the boundary, it decays exponentially. So at the surface, you have a constant magnetic field which decays into the semiconductor, superconductor inside. And then you have some current density due to this magnetic field inside the superconductor. So just by presence of mere field there, magnetic field, we have some supercurrents inside the superconductor. Today, I'm going to extend it further. So we are going to talk on the thermodynamics of the superconductors. So, so let me read this slide first, and I'll proceed with you. The transition between the normal and the superconducting state is thermodynamically reversible. Thus, we may apply thermodynamics to the transition, and we thereby obtain an expression for entropy difference between normal and superconducting state in terms of critical field versus temperature. So this is a reversible phenomena. I mean, you have a control on yourself, whether you can change the temperature or magnetic field, you can reverse from superconducting to normal, normal to superconducting. So it's a thermodynamically reversible process. So we will now try to understand its entropy, specific heat of the superconductors, which will help us understand the further properties. And we treat type 1 superconductor with a complete Messner effect where B is equal to 0. We can see that the critical field Hc is a quantitative measure of free energy difference between superconducting and normal states. So now we will define certain terms like stabilization energy in the superconducting state, just from the preliminary idea of magnetism, which you already have. So now look at this slide here. And here we are talking about in the magnetic field, the stabilization free energy is found from the value of applied magnetic field that can destroy the superconducting state at constant temperature. Consider a work done on a superconductor when done on a superconductor that is brought reversibly from infinity to a point R in the magnetic field. So you can see in the diagram below, there's a magnet lying here where my cursor is, and because this is North Pole and it's producing a magnetic field. And you are bringing some superconductors from the infinity. So these are the definitions of work done in the magnetic field: magnetic induction multiplied by magnetic field. Just like, you know, mu naught H or mu naught B is the free energy. So this is how it is defined, the work done, the basic definition, that you bring a superconductor to in a field. Now when you are saying bringing a superconductor, try to understand that you have kept its temperature low so that it is a superconductor. So you are trying to bring entire thing in some container where temperature is kept low so that it is still a superconductor. As you bring it from infinity to certain point, applied magnetic field. So there is a, here this arrow is showing M in opposite direction, because we know that superconductors are diamagnetic. We learned it, and that means the applied field is equal to the induction in opposite direction. So as the total induction is zero, basically magnetic moment produced in the opposite direction to the applied field cancels and the induction is zero. So that gives us that B is equal to minus BA upon mu naught. So from the definition, the work done of the free energy is minus m dot dVA, and from the above equation of this induction, sorry, here this B should be m basically. I think this is there is some wrong in this. This is m. This B should be m here. So you replace the value of m, and that is what you get. So in a superconducting state, the work done is basically this much, dFs. Now you know this, that with the superconductor there is a associated critical field. Now when you are far, magnetic field is very weak, and you are below critical field, so it is still a superconductor. But when you bring it very close to the magnet, it means your magnetic field is increasing and your applied field is equal to some critical field. So at the critical field, you can go both way. You don't know whether your system is actually superconductor or a normal conductor. It can be both ways. Just slight shift of magnetic field can take it to a normal conductor and superconductor. So we say that this is the equilibrium where both phases exist. Both phases exist means superconducting phase and normal phase. Both are coexisting. So coexisting means just slight change of magnetic field. You can go in either direction. Either you can say this is a normal conductor and it's a superconductor. You are just standing at the boundary. So at the boundary, it is better to say that both phases are coexisting. Okay, so these are just some basic equations derived from the basic definitions of thermodynamic potentials. So now integrating. Now the last equations we have integrated. This equation in the last we integrated, and the field is from 0 to BA. As we have seen that you are bringing it from the infinity where field is 0 to a field A. So this is a definite integration on the left hand side, and on the right hand side you have BA square upon 2 mu naught, or this equation can be written like this. Okay, so I'm just going slow. Take your time to understand. You look at the equation and integrate this equation, and you see it's you are having magnetic field 0 at the infinity, and when you bring it near the magnet, it is A. So that's how Fs BA minus Fs 0, and that's how you know the free energy at applied magnetic field is free energy at where there is no field plus this factor. Okay, so now what next? It says a critical field, normal and superconducting phase. At critical field, normal and superconducting phase coexist, so the free energies of the superconducting and the normal state are equal. So this is an assumption basically, that at the critical field, where you are just at a point from where you can go either to the normal state or you can go to the superconducting state just by choosing your direction. So at that point, because this is a state of equilibrium, at this point the free energies of the normal and the superconducting states are equal basically. That's what is the assumption from the thermodynamics, and this is also seems plausible assumption, because you can see that basically you are changing nothing as terms in terms of the internal properties of the semiconductor, electron densities, their lattice spacing, and all sorts of electronic structure. They remain intact. So when they remain intact, that means their free energy should be equal at that temperature, whether it is in superconducting state or it is in normal state. So subscript here, it tells us the normal, and sorry, the subscript N means normal and S means superconductor. Okay, now in the below there is some argument, and it says that in case of non-magnetic material, we may neglect the susceptibility of metal in normal state. The energy of the normal metal is independent of the field. So what it is trying to say, that if a material is non-magnetic, the materials are defined, as you say that we talk about paramagnetic substance, ferromagnetic substance. So when we say magnetic substances, generally we are talking about ferromagnetic substances where induction is very large. If you put them in a field, they produce a very large susceptibility. On the other hand, there are other materials, let us say they are paramagnetic materials, and their induction is very weak. And in some cases that can be even very weak, so that you can neglect. It means whether you apply a field or you don't apply a field, the free energy is the same. So here when we are taking this equality, we are neglecting that small change in susceptibility due to the application of magnetic field, because our system is non-magnetic and susceptibility is very weak. So this is an assumption that here you have BAC, here you have 0, and so in a normal state, so this, remember that it is in the normal state when it is not a superconductor, it is just a normal conductor, so a non-magnetic material. So whether you apply a field or you don't apply a field, it doesn't matter. Just like you can see that if I speak just to explain you that, for example, you have a non-magnetic material, let us say a plastic, you watch you are having made of plastic, you put on the table and you try to bring magnet near it, magnet won't attract it. You have some wood pencil and you try to bring a magnet near it, it won't attract. Possibly nothing will happen inside the wood pencil, because the system is non-magnetic. It will not respond to the magnetic field in the normal condition. So that's what it is told here, that Fn, BAC, Fn0, either you apply magnetic field or you don't apply, this is the same stuff. That's what this equation tells us. Okay. So now from the last two equations, these two equations are telling us this equality. This is, you can see, this is from this last two. You remember this and you remember this, and now you come here. So this is basically at a critical field, the free energy of superconducting state and normal state are the same. That was the first equation, and this was already derived. And as we know that from the second equation, so Fnbac is equal to Fn0, because if you apply magnetic field or if you don't apply in a magnetic material, it is the same. Okay, so Fn0 minus Fs0. So that is what. So stabilization free energy of a superconducting. What we have got now out of this equations, basic definitions of the thermodynamic potentials, and using the definition of energy from bringing a material from infinite to near the magnet. So we calculated the work. So this is what is called as the stabilization free energy of the superconducting state. It means it is comparing the free energy in the normal state when there is no field. So zero inside means there is no field. And when it is superconductors, in the absence of magnetic field. So this equation is telling us, in the absence of magnetic field, what is the change in energy? It means if you drive the system from normal to the superconducting state by applying a temperature, by reducing a temperature uh, in the absence of magnetic field. So zero means you don't have magnetic field. Then this is the stabilization free energy, which can be expressed in terms of क्रिटिकल मैग्नेटिक फील्ड। क्रिटिकल मैग्नेटिक फील्ड के में हम इसको एक्सप्रेस कर सकते हैं कि जब नॉर्मल से सुपर कंडक्टिंग स्टेट में जाते हैं तो जो स्टेबलाइजेशन एनर्जी है वो क्या है, कितना उसमें चेंज आता है एनर्जी में, बेसिकली दैट्स व्हाट इज ट्राइंग टू से। एंड now this is the famous equation of the free energy and the entropy in the superconducting transition. So now we are from using this definition, we want to understand the entropy of the superconducting state. Entropy of the superconducting state is another important thermodynamic parameter. So F is equal to delta US minus T delta S is equal to. So if you differentiate this with respect to T, you get minus dF upon dt. Here du being the energy, so this is some potential energy coming out from the interactions, let us say electron-electron interactions, electron-lattice interactions, and you have core atoms, ions in the system. So this potential energy, this is constant actually. It's assumed as a constant of temperature because this is just a Coulombic interaction between the particles. So the density of the material is same as, so that's why this is not dependent on the temperature in that sense. And we have now S is equal to minus dF upon dt, or if we now write dF upon dt from this equation. There is an equation above, okay, I should give it some number maybe. So if you differentiate this with respect to T, this is what you get. So entropy is minus mu naught Hc dHc upon dt. By differentiation you will get. I'm just stopping here for 1 minute so that you can understand what has happened using these equations. This equation has been a dF upon dt. This has been differentiated. Okay, you can forget about delta because you can treat this as entire F when you want to say that this is the free energy. Okay, so when you do dF upon dt, this is what you get. All right, in terms of critical magnetic field, we have defined our entropy now. So now we are in a position to understand the entropy of the superconductors, discuss the entropy. So delta S is basically entropy in the normal state minus SS entropy in the superconducting state. So that gives us minus mu naught Hc dHc upon dt. Now this dHc upon dt, the sign of this will determine whether this entropy is positive or negative. So now it is not difficult to understand that normally in the normal state, this has to be the state of higher entropy, and the superconducting state, which is known to be ordered state, is having a less entropy. So this has to be with the positive sign. So you can see minus here, but because this is negative, this becomes positive. Well, you can see that this is a relation between Hc and T. So from where we understand that this is negative, this is already experimentally determined, this relation between critical magnetic field and the temperature. This is well known as we have already seen it from the experiment. So if you look at this curve, anywhere you find out its slope is negative. Okay, if you have a positive slope, means curve should be like that. So curve like that will have a positive slope, and if it is like this, it is a negative slope. So this curve has a negative slope. So negative slope means this will always be positive. So means when you go from superconducting to normal state, you increase the entropy, or the entropy in the superconducting state is lower than if it is in normal state. So normal state के comparison में superconducting state में entropy कम होती है. अब इसको इसमें आप यहाँ देख सकते हो कैसे प्लॉट की गई है. ये entropy है, ये temperature है, and then you are reducing the temperature, and if you keep the material in the normal state, it would linearly decrease like that. Now how can you do that? That if you can still reduce the temperature of the system, but it is a normal conductor, it is not a superconductor, तो आप कैसे रोक सकते हैं इसको superconducting होने के लिए? Magnetic field apply करके. As you know that magnetic field also breaks the superconducting state. So you apply a magnetic field higher than critical magnetic field. So whatever low temperature you go to, it will always be a normal conductor. So up to 0 Kelvin, you can see what is the normal entropy. Now in the superconducting state, you can see that this is merging here at this point and also at this point, and in between there is some point where the difference is maximum. It is because you can see here this entropy is a product of Hc and dHc upon dt. So if you come here, Hc is maximum but dHc upon dt is minimum. यहाँ पे slope सबसे कम है, magnetic field ज्यादा है. कम क्या है, यहाँ ऐसे जाके slope 0 हो गया, तो एंट्रोपी डिफरेंस ऑलमोस्ट 0 हो गया. तो यहाँ देखो नॉर्मल और सुपर कंडक्टिंग स्टेट में इस पॉइंट पे डिफरेंस 0 हो गया. ऐसे ही अगर हम यहाँ आएंगे तो यहाँ स्लोप बहुत हाई है लेकिन मैग्नेटिक फील्ड 0 हो गया, Hc 0 हो गया. तो 0 हो जाने की वजह से फिर इनके बीच में जो डिफरेंस है वो 0 हो गया इस पॉइंट पे आके. जहाँ सॉरी पहले वाला ये पॉइंट था जब हम इसकी बात कर रहे थे, ये इस पॉइंट पे, और ये 0 वाला पॉइंट ये यहाँ है. So you can see that comes a point in between where there is a large difference in superconducting state and normal state. The large difference in the entropy. So superconducting state is a state of lower entropy as compared to the normal state. So that is how it is regarded as more ordered state. So superconductivity, in terms of electronic configurations, in terms of the entropy, it is regarded as a more ordered state, because as you know from the basic definition of entropy, because larger is the entropy, more disordered the system is. So lower entropy means system is more ordered in the superconducting phase. Okay, so I hope this is clear. Now I will maybe just go beyond slightly, and I will one day have just an interaction session. So in this format, it is very difficult, to have questions, counter questions in between, because one is the time limit of this 40 minutes, and that it will be difficult. So I request that you keep writing your questions. You just note down your questions whenever they arise to you, make their file and give it to someone, maybe Tarun, or send a copy to me entirely. And one day I will sit just to answer your questions. They can be any type of very preliminary questions to any kind of questions that comes in your mind. You write them and send them to me in a file, so that one day I will sit just for the interaction class and answer your questions. So right now you can just note down your questions if they are arising. Now let me now proceed. Now we are ready to talk about the specific heat of superconductors. Now these are just from the thermodynamics relations, and sorry. Okay, so this is from the thermodynamic relations. This is the definition of entropy, and here we multiply by T. So this gives us heat, Qn, like this. And in this, if we differentiate, let us say this with respect to T, this equation above, ds upon dt, ds s upon dt. So there is a differentiation, and you multiply with T on this entire equation like this. So this is what we get, and this is just from the above. Following this, you can do it yourself. I'm not spending much time on this, because finally I will share you my slides. So when the lecture series is over, I'll give you the slides so that you can understand these equations yourself. These are simple solutions, nothing much is there. You can do it very easily. Now, so you can see Cn minus Cs is equal to minus mu naught T dHc upon dt square, because this is a differentiation by part. So first you differentiate first term, second as it is, so it comes in square. Now you leave HC as it is, and this is the second derivative. Now here this the second derivative term will become 0, because at T is equal to Tc, Hc is equal to 0. You know, at the critical temperature Hc की value 0 होती है. You can understand that यहाँ पे critical temperature पे Hc की value 0 है. When you put T is equal to Tc here, this become 1 minus 1 and it's 0. So this is 0. अगर ये यहाँ 0 आ गया इसमें, तो ये सारा term 0 हो गया, and you are just left with this term where you have specific heat. This is specific heat of electrons, because there is one contribution of specific heat comes from the lattice, and that we are not, of course, talking here. The lattice is specific heat. So now we can see that. Now first we had a first derivative of this curve. Now you look for the second derivative of this Hc with respect to T. So that gives us, as you can see the curve here, there is an exponential rise and then there is a sudden change. So at the transition, there is a sudden change in the specific heat. You will have, in the superconducting state, you have more specific heat as compared to the normal superconductors. So this you can understand also from your, if you take the second, so this is basically the first derivative of dH upon dC. If you take this, the second derivative, you will see that constantly the slope is increasing. From here, whatever the slope is, at every next point, the slope is increasing. So this is the second derivative. So that's what you get. You see here, the slope is increasing. And when you go from normal to the superconducting state, you see the jump in the specific heat or the superconductor. So this is also experimentally measured. This we have calculated from the thermodynamic potentials, but that is also specific heat can be measured using a calorimetric experiment. Means you measured how much heat is transferred to the system in a one temperature. If you increase the temperature of the system by 1 degree, how much heat is given. So with that measurement, it can be easily measured in any calorimetric experiment, specific heat. So this calculation and this measurement are quite in agreement for the superconductors, and measurement also says that specific heat takes a sudden jump when you go from normal to the superconducting state. So now if you do some slight mathematical modeling of this, basically now if you would like to fit it with a curve, it looks like an exponential increase. So this is an exponential increase, and you can fit it with some sort of exponent here, where beta is defined as 1 upon kBt, and delta is energy. So it's some sort of energy gap, which has been talked of as an energy gap at the Fermi energy at the superconductor. तो यहाँ हम अगर assume कर लेते हैं कि कोई energy का gap है. These are field levels and these are empty levels. As you know that when you talk about let us say metals, and at when you want to find out the ground state of that metals. So what is the ground state of that metal is that you keep on filling that energy levels, and when you are exhausted with these number of electrons in the system, because they are constant, you have definite number of electrons, at some point of time your electrons will be exhausted if you keep filling this, and you reach up to certain level. So this level is defined as the Fermi energy. So basically this equation tells us that to go from here to here, there is a certain jump, there is certain gap in the energy, and this is called a superconducting gap here. This delta is telling us that why this is following this exponential relation is because electron will need some little energy from go from this to that. It is just like a, you can think of in semiconductor systems, you have a band gap and you need some energy from electrons lower to jump the electron at the higher state. But there, the band gap is very high, of the order of 1 electron volt, and that is of the order of 1 electron volt. But here you can see it is 0.165 milli electron volt for mercury. Milli means 10 raised to the power -3. So this gap is very, very small. And that is why even a slight temperature, very low temperature, such as 4.2 Kelvin, you can take the electron from field level to the upper state. And this gap is seen that it changes with the temperature. That's what this lower curve is telling. That when you are near absolute zero, this gap is maximum. And when you increase the temperature, this gap here is reducing. And at transition temperature, this gap is also zero. So this superconducting gap is disappears. So this mathematical fit or to this equation, this exponential changes, they somehow tell us that there should be some superconducting gap at the Fermi energy, and then only this kind of equation can fit with it. And you need electron. The electrons need certain energy, though it is very less. You know, this is a milli electron volt (MeV) for electron from jumping to here to there. So the crux is that, you know, this gave us some hint that at the Fermi energy there needs to be some superconducting gap. And this we have to see further, whether what kind of theories can explain this superconducting gap. And further, I think when we will be talking about the BCS theory of the superconductivity, I will take it up. So now I leave it here because this time is running and I cannot complete this BCS theory. Next, I will discuss this BCS theory after this. So we understand this up to the superconducting gap. There is a superconducting gap, and that we have learned from the specific heat measurement. From the potentials, we also saw that this kind of nature of the specific heat should arise. So now I think I just stop sharing now, and you can, if you like, for maybe 1 minute, you can switch on your video and audio. I have kept this option open for you, that you can switch on your video, audio you like. And I'm going to end this session maybe in 1 or 2 minutes. So okay, I have some chat. I can see that the chat there is a good morning, and okay, just some students are not able to connect. They require host permission. So I don't know, because why it is happening. They require host permission. Let me see if manage participants. So okay, so I think there was some change in the setting. Anyway, what I will do is I'm going to the session is recorded, and I'm going to